Welcome to The Explainer. I'm absolutely thrilled you're tuning in today because we're tackling one of the most critical challenges in the entire generative AI space right now. If you're a system architect, a developer, or really just someone fascinated by how AI is actually deployed in the real world, you already know the core struggle. How do we build generative AI applications that are reliable, blazingly fast, and cost-effective? Well, today, we're going to trace this incredible evolutionary journey in system architecture to answer exactly that.
Okay, let's dive into this. Have you ever stopped to wonder how an AI actually reasons over documents it's never even seen before? Think about a private internal company wiki or a business's freshly released quarterly financials. If those documents weren't in the massive dataset the AI was originally trained on, how does it know what to say? The model literally has to fetch that information from somewhere at the exact moment you ask your question.
And that brings us right to the root of the problem, the knowledge cutoff. This is just a fundamental limitation of parametric neural networks. Parametric basically just means models with fixed, static, pre-trained weights. They simply cannot natively access proprietary or real-time data beyond the date they finish their training. It's like their brains are frozen in time. Because of this gap, system architects have historically had to rely on complex dynamic prompting to forcibly inject external information into the AI's view exactly at inference time.
So, here's our roadmap for today's explainer. First, we'll look at the LLM knowledge gap. Number 2, RAG, the retrieval paradigm. 3, long context, the brute force. 4, CAG, the caching revolution. And finally, number 5, which approach wins. Let's get right into it.
Section 1, the LLM knowledge gap.
So the absolute easiest way to think about large language models is to imagine a truly brilliant student who only knows what was printed in their original textbooks. Now, to overcome this barrier of static training data and get that brilliant student to answer questions about today's news or your private files, we actually have to go fetch that new information for them. And over the past several years, the AI engineering community has developed 3 primary paradigms to manage this whole information fetching process.
Moving on to Section 2, RAG, the retrieval paradigm.
So, first formalized by Meta AI researchers back in May 2020, RAG represents the traditional approach to integrating external knowledge. To stick with our student analogy for a second, RAG is essentially the ultimate open book test. But for every single question you ask, the AI actually has to get up, run to the library, find the exact right page, read it, and then run back to you with the answer. Now, what's really interesting about this slide is the multi-step ingestion and real-time query flow that makes this happen. Offline, you break your documents down into smaller chunks, you embed those chunks into mathematical vectors, and then you store them in a specialized vector database. Then, at query time, the system takes your question, turns it into a vector, runs a real-time nearest neighbor search to find the most relevant chunks, and injects them right into the prompt for the LLM to read. It's a highly dynamic, very active process.
But you know, here's the stark reality. RAG can break down pretty fast in production. For one, fixed-size chunking often splits paragraphs right in the middle of a thought, so you completely lose vital context. On top of that, single-shot retrieval might grab data that uses similar words but is totally irrelevant to your actual question. Add in the high latency of doing this all in real time, plus the massive system complexity, and you've got a real headache on your hands. In fact, industry analysis show that around 72% of enterprise RAG implementations either fail or underperform in their very first year, specifically because of these structural flaws.
Which brings us to Section 3, long context, the brute force approach. Yes, RAG is incredibly complex and error-prone. But what if we just skipped the entire retrieval pipeline altogether? What if we just stuffed absolutely everything into the prompt? We are now seeing models with utterly massive context windows. Models like Gemini 1.5 Pro or Llama 3.1 boast context windows up to 1 or even 2 million tokens. To put that into perspective, that is the equivalent of handing the AI 20 full-length novels and asking it to speed read all of them before answering a single question. No chunking, no vector database, just pure brute force processing power. However, just because you can feed it 20 novels doesn't mean it's going to remember them all perfectly. While long context allows for incredible deep cross-document reasoning, it suffers from some pretty severe cognitive limits. Researchers have documented this lost-in-the-middle phenomenon, where the model's performance basically follows a sharp U-shaped curve. It remembers the beginning and the end of the giant prompt really well, but completely fails to recall information buried right in the middle. Plus, processing millions of tokens for every single query is just incredibly computationally expensive and agonizingly slow.
Section 4, K, the caching revolution.
So if RAG is the student running back and forth to the library, and long context is the student trying to speed read the entire library right before answering, CAG is the revolutionary student who perfectly memorized the textbook the night before the test. No library trips needed, and no last-minute cramming. And this brilliantly illustrates the architectural shift. Traditional RAG relies on all these active moving parts and retrieval latency during real-time inference. But with CAG, active retrieval is just completely gone. Instead, the knowledge is preloaded offline and sits in a static context cache, waiting directly alongside the query.
Here's exactly how that CAG workflow goes down. In Phase 1, you take your static dataset and you preload it. In Phase 2, you run that combined prompt through the model exactly once to pre-compute a key value or KV cache. This essentially captures the model's deep internal understanding of the text right in its attention layers. Finally, in Phase 3, when a user actually asks a question, the AI queries against this warm pre-computed memory state. It generates a response utilizing the entire document collection instantly, without a single external database lookup.
The performance data on this is absolutely staggering. Because CAG completely eliminates retrieval latency, the speed-up surge is massive. For a larger document set of about 85,000 tokens, standard RAG took over 94 seconds to process. CAG handled the exact same task in 2.33 seconds. That is a 40.5 times speedup. You get lightning-fast responses, you maintain or even improve accuracy by completely eliminating retrieval errors, and you drastically simplify your system architecture.
Finally, Section 5. Which approach wins? So how should you actually build your applications given these three powerful tools? Think of this as your practical tool belt cheat sheet. RAG is absolutely still indispensable for massive datasets. We're talking millions of documents or highly dynamic data, like a constantly changing newsfeed or live inventory where you need those frequent updates. Long context, on the other hand, is your go-to for deep, exhaustive reasoning across a single massive input, like analyzing a 500-page legal contract in one go. And CAG? CAG is the absolute winner for static knowledge where you need lightning-fast response times. Think stable technical manuals, standard operating procedures, or fixed HR guidelines.
So, the crucial point is that the future of system architecture isn't binary. It's not one or the other. The best enterprise systems aren't picking just one. They're intelligently combining these paradigms based on the specific query pattern. We're seeing tiered routing, where CAG handles the core, frequently accessed knowledge instantly, while RAG is kept on standby for real-time edge cases. Or even the self-route framework, where the AI actually self-reflects to try a cheap, fast RAG retrieval first and only falls back to expensive, long-context processing if that initial retrieval misses.
As you look at your own generative AI deployments, or even just the tools you interact with every single day, I want to leave you with his final, provocative thought. Is the system you're building frantically fetching information over and over, or is it truly remembering it? Understanding the difference between RAG, long context, and CAG is absolutely the key to building the next generation of seamless, instantly responsive AI. Thank you so much for joining me for this explainer. Keep exploring, and I'll catch you on the next one.